Thank you so much. Really excited to be here. Really excited to actually get to talk at RustConf. Little nervous. It's always a little bit exciting to talk about a not Rust programming language at a Rust conference. But I'm going to try and do my best. Just as a little bit of background, I've been in the programming languages and compiler space for quite a while. I spent a decade working on the C++ standards committee for Google, trying to make C++ better. I've worked on LLVM and Clang a whole lot. Right now, I am one of the leads for Carbon, but I also kind of work at Google on our central programming languages and compilers team. We have to support a whole wide range of languages, Java, Kotlin, Python, Rust, as well as C++. But today I want to talk about Carbon and Rust, and more importantly, I want to talk about memory safety. Now, when I talk about memory safety, what do I actually mean? What do I mean by memory safety everywhere? Well, I hope folks here are fairly familiar with why memory safety matters. If you're not, this remains kind of the dominant source of security vulnerabilities in C and C++ software. The only durable solution we found to these vulnerabilities is to write new code in memory-safe languages, and that does work. And I think there's been some skepticism, maybe not in the Rust community, but outside the Rust community about whether this works. I really encourage people to check out this blog post from the Android people. They have some of the best data I've ever seen about just how effective it is to reduce vulnerabilities when you actually deploy Rust into a system and start moving your new code over to it. I also suspect that folks in this room probably know how to write code in a memory-safe language. Maybe some of you do, because you can write it in Java, right? Or Kotlin. Maybe you could write it in TypeScript or in Python. But for this room, you probably want to write it in Rust, right? Rust is great. So I can't be talking about the memory safety part of this. That's not the interesting part of this talk. It's the everywhere that's the interesting part. That's actually what I want to really focus on, because there is a lot of software in the world. And it's not in isolation, right? It's all part of an ecosystem, right? With my favorite ecosystem diagram, because this is what most of our software ecosystems look like. And whenever we try and move some piece of this from one programming language to another, we have to actually integrate it into the rest of the ecosystem. You can't move things in isolation. And that means that trying to get software into a memory-safe language, interop is always going to be key, right? Interop is kind of the dominant thing that allows us to really adopt memory-safe languages. And interop can come across a wide spectrum. In Rust, you have things like externc and bindgen. The CXX create all kinds of low-level tools. There are higher-level tools that people are looking at, such as crewbit, that try and take interop a lot further. But there's not really anything beyond crewbit, right? And I think there is kind of an extreme. This is really a spectrum we're talking about. And I think of the spectrum as the spectrum between greenfield and brownfield. But greenfield and brownfield can be a bit overused. It can be a bit generic. So let's try and give some really crisp definitions for what we mean by greenfield and brownfield. So in greenfield, what I'm really talking about is new code that is less tightly coupled to an existing C++ ecosystem, right? Maybe it has really strong abstraction boundaries. Maybe the API design was really excellent. It has a modular architecture. It's very easy to move that code to a different programming language without being tightly coupled to existing C or C++. On the brownfield end of the spectrum, we're talking about software that's more tightly coupled. Maybe it has a really large API surface. Or maybe it uses all of the language features that anyone has ever thought of and is template metaprogramming like 8 layers down. Who knows why it's tightly coupled? The key is that some software is deeply and tightly coupled to an existing C++ ecosystem. Right, and basically Rust has started off in this greenfield space, but been marching steadily towards the brown field as more and more advanced forms of interop are available. And this is fantastic. The question that I am left with is, can it ever get to the furthest extreme? Because I don't think this diagram is to scale. I think this is actually a massive, massive spectrum. And I think that the gap here is huge. And so for me, what I really want to see is, can we take a more kind of maximalist approach to getting memory safety that is going to have a better chance of covering all of the spectrum of software? Ideally, we would add memory safety to C++. This is actually the obvious way to get the brownfield extreme of C++ code to start being memory safe. This is a fantastic idea. Several people have had it before. I definitely did not come up with this. A long time ago, Dana Jansen's on the Chrome team wrote an analysis of what adding memory safety to C++ might look like. Since then, Sean Baxter has actually implemented a pretty clear version of what memory safety might look like if added to C++. This is possible, but unfortunately, I don't think this is going to happen. The C++ Standards Committee has pretty clearly moved in a direction that says they're not going to ever get to proper memory safety. That's a whole separate talk and a contentious topic, but at the end of the day, I have no confidence. I do not see a way that we will successfully add memory safety to C++ as it is. And that's sad, first off. But secondly, we still need a plan. Right? Like, we still have to go after this brownfield of software. That software is not going anywhere. It's not getting less valuable. People aren't writing less of it, sadly. That software base is actually growing, even in the brownfield. And so I still want to find a solution. Fortunately, we have figured out how to evolve a language in kind of a new direction, but optimized as far as possible for the brownfield in the past. C to C++, for example. Figured out exactly how to do this. We've also seen this in JavaScript and TypeScript. We see it in Objective-C going to Swift. We see it in Java going to Kotlin. And this is where I see an opportunity, where we can go from C++ to something that is tailor-made for the brownfield, right? That is trying to target this specific use case. And this is the use case that I really see for Carbon. Carbon allows us to have an incremental path to evolve and migrate off of C++, to incrementally add memory safety to existing software and prioritize the most brownfield use cases. Right? If you go back to my spectrum, my view is that like Rust is kind of moving in one direction and Carbon is moving in the opposite direction, from the opposite extreme. And I really like this because I feel like this gives me much more confidence that we can cover the entire spectrum. Right? Because we're starting at the polarities and we're moving inwards, rather than trying to reach from one to the other. And so I think this is a really exciting strategy. But it does mean something interesting. It means that Carbon and Rust are incredibly different. And I thought I would take most of the time today to actually examine that difference, because I think it's interesting to see what goes on when you design a programming language completely around the brownfield. How different does it end up looking? Like, how many things change? And I figured this is a programming language conference, so let's look at some programming language stuff. Now, I'm going to show a bunch of Rust syntax here. I have to admit, I am not the world's foremost Rust expert. I've dabbled in Rust, but I'm not an expert. Huge thank you to a bunch of my colleagues who helped cause the Rust code to even be slightly correct here. I'm sure I managed to like edit it or make a mistake with it, and sorry, that's my fault. But let's look at some Rust code. The syntax is fairly easy to understand, right? You have functions, local variables, you can call methods on them, you can print them. And Carbon syntax at this level is going to be fairly similar as well. There are differences, but they don't really matter. We have functions, you have local variables, you can call methods on them, you can print them. This is not like wildly different. So the first place where I start to see really big differences is around code organization. How do you structure your software? So let's take a Rust code. I ripped all of this off terribly from the Rust documentation about like the front of house of a restaurant, but I really like the example. And I've tried to actually break it into a lot of different files and show how it might be organized in an interesting way. So we have some table type here in one of our modules. Right? In a separate module for hosting, we actually call a method in the serving module of the crate, right? We add a new table as being seated to the serving module, right? We also provide a method to the serving module to clear a table once it's ready for us to seat people at it again. And then in the serving module, right, we're going to provide that add method, that add table function that the hosting module calls, and we're going to ourselves call clear table when a table becomes clear and we can actually seat new guests at it. So the interesting thing here is this is actually a cyclic dependency, right? Like you've actually kind of entangled these modules. Each one is calling the other. And Rust is fine with this because it does crate at a time compilation. Like this works great. This is a wonderful, simple way to organize code. I love this. And I'm not being sarcastic in the least. This is a fantastic model. Carbon, though, takes a different approach because crate at a time compilation can reduce separate compilation. right? It's a larger granularity of compilation. One of our priorities with Carbon was to not regress the ability to do separate compilation that we have with C++, because large-scale code bases in C++ are often oddly dependent on that capability. And so in Carbon, you can't structure the code this way. You actually have to break it apart. You have to break the cycles and form a DAG. Right? This might look like having a table class and having the two functions in that library. Right? And then we can import the library. We can call the functions. We can import the library in another place and call the function. Right? Not a very big deal. This doesn't seem like a big deal. But it gets a lot more than that. Because the other big thing that C++ provides for separate compilation is the separation between interface and implementation at the physical level. And Carbon tries to support that as well. You don't have to define all of your functions in the API file. You can have forward declarations and out-of-line definitions. So here, we're not going to define these two functions. We're just going to forward declare them. Okay? This doesn't actually define them. And then in a separate file, an impl file, right, we're going to go and provide the definition for each of these functions. And now in the hosting libraries API, we don't need to import table at all. None of the API depends on the table type. And so we haven't just given ourselves separate compilation. We've actually reduced the dependencies of the API. Right? We're actually using physical separation of implementation to also separate implementation dependencies. Right? It's only down in the hosting implementation file that we import the table library, and we actually call its function. This is kind of a trivial example, but you can see how this can scale up and provide really, really advanced build system parallelization, build scalability. But it comes at a cost, because this is way more complicated than Rust's model. Okay, we're dealing with forward declarations. We have to match those to definitions. We have to line them up and make sure they all work. We have to teach the linker how to assemble all these things. This adds a huge amount of complexity, and that's not a joke, right? So we're making a trade-off here. We're getting this very advanced separate compilation, but we're paying for it with complexity. And you can see where this complexity comes from. It's not just out of thin air. We've tried to really follow C++ and the best practices we see from C++ at scale. You've got some large library like Absil or SQLite, right, that turns into a package, right? It's like a unit of versioning or distribution. You've got a header file that turns into an API file. That's the unit at which you can import things, right, or include if it was in C++. You've got C++ source files, and those turn into impl files, right, which gives you physical separation of implementation and dependencies. It's optional. You don't have to use this, but it's available when you need that flexibility. We even support very advanced dependency pruning. So C++ has this pattern of forward declaration headers, where you can declare a whole bunch of things as forward declarations without any of the definitions, and this allows consumers of a very wide API that only consume it sparsely to have sparse dependencies as well. Right, and we even have a feature designed around this, right? And all of this is basically motivated by patterns that we saw emerge and get used in C++. We want to make sure we can kind of meet code in that organizational scheme. Let's look at types. Types are pretty simple, right? You've got up, you've got a field, we can implement some methods on this, like an increment. Increment seems like a good method to implement on this. And then initially, again, Carbon looks fairly similar. There's a little bit of difference, but nothing very scary here. All right, we have the class called up. We have a method called increment. We have a field. We actually put the method inside the class in Carbon. This kind of just follows the C++ organizational scheme. I don't think one of these is better or worse than the other. I don't think there's like an especially important trade-off here, but clearly Carbon is trying to skew as close to C++'s organizational patterns and idioms as it can. But again, we don't stop here, right? Carbon also supports inheritance. And so we have base classes, and we have virtual functions, and we have protected fields, and we can derive from base classes and override virtual functions and add new virtual functions. And like all of this stuff is complexity that the Rust core language just doesn't have, and it doesn't have to deal with. If you really need to express some pattern like this, you can express it. There's the hash-derived macro. There are other things you can do to kind of get the functionality you need. But the core language stays simple and minimal. It doesn't have all of this. Carbon, on the other hand, wants to really meet existing C++ APIs where they are. And if you have an API that's designed around inheritance and extension, Carbon is going to allow you to do that. We can actually inherit across the Carbon C++ boundary, do virtual dispatch across it, the whole 9 yards. Let's talk about functions. Right? Maybe you want to do 2 different appends with 2 different types, integers and floating points. You write 2 functions in Rust. It's not a big deal. Right? These are simple, easy to understand functions. But in C++, this would probably be an overload set. Well, Carbon, again, is going to choose to embrace that complexity. And so Carbon has built in function overloading to the language so that we can directly model overload sets that you would find in C++. Right? We say that this is an overload, and we list the 2 signatures that we can implement here. Right? This is a ton of complexity. If folks have dug into type systems and programming languages, having overloads, potentially overloads with different return types, and all of the consequences of that adds a tremendous amount of complexity to the language. Right? Rust can, again, similar to inheritance, it can express similar things. You can have a trait, and you can call a generic function on that trait, and you can implement it differently for different types. There are ways to kind of get at the same functionality here, but it keeps the core language simpler. Whereas in Carbon, we're kind of baking in support for this really complicated part of the core language because it's something that is foundational in C++ today. And a bunch of C++ APIs are designed around it. Right? We want to make this much more seamless. This pattern is pervasive. I had 2 more sets of examples. We don't have time for all of them. But you can see this come up when you look at generics. Because Rust has generics. It's wonderful. Carbon has generics. Unfortunately, Carbon also has templates with its generics, with full instantiation. It has specialization. It has all of that complexity as well. You can see it with conversions. In Rust, all conversions are explicit. There's no 2 ways about it. They're just explicit conversions. In Carbon, we actually support implicit conversions, because C++ has implicit conversions, and APIs are designed around them. So we're trying to figure out how to make that work. Each time we have this trade-off where we're taking on complexity in order to meet kind of API designs and code organization in C++ where it is at today. But it comes at a cost. But we're supposed to be talking about safety, so let's actually dig into safety a little bit. Fair warning, this is still very new. We've started really fleshing out the safety design in Carbon, but I mean started. Everything here is as unbaked as it gets. The syntax is made up on the fly. Please do not hold me accountable for all of the mistakes or things that end up changing here. But I wanted to give you all a flavor of where we're going with safety, because I think the same pattern is going to emerge. And let's start by looking at mutability and exclusivity. It's just a good place to kind of see this pattern emerge in safety with Carbon and Rust. So with Rust, things are very simple. You have shared immutable borrows, right? You have mutable exclusive borrows. These 2 are the two whole concepts you have. You can have as many X's as you want. That's no big deal because they're immutable, it's shareable, it's easy, but you can't mutate through it, of course. It's not too surprising. You can mutate through Y because it's a mutable borrow, but you can't pass Y twice like this because that would make it non-exclusive. No big deal. This is stuff you all are familiar with. So Carbon, we're expecting to have a somewhat more complicated model. Okay? So we're going to have something that's very analogous, at least here, it's analogous to how shared borrows work. We're calling them immutable values, but we can think of them similarly, right? And we're going to have something else called reference bindings, right? And why is going to be a reference binding? And with this immutable value, you can make as many of them as you want. You can copy them freely. This is fine. This works just like shared borrows in Rust. But you can't mutate them. Now, the reference binding you can mutate through. It's a mutable reference to some other state that you can mutate. But the really interesting thing is that when you call this gmutate, you can pass multiple reference bindings to the same object. This is a non-exclusive reference binding, okay? And that means that in Carbon, we're not going to just have the 2 states that we model in Rust of shared, immutable, or exclusive mutable. We're going to model more states, which is fundamentally more complex. We're going to model shared, immutable, right? We're going to model this mutable, non-exclusive thing, and we have to model exclusive, because exclusive still comes up, right? This is going to be a fundamentally more complex model, but it is also going to allow us to express more patterns and still prove them safe. Now that may sound good, but let's actually look at what motivates this. I want to deep dive into exactly why we think this is going to be a compelling additional complexity to spend in the language. And so these are real-world use cases. These are actual real code. So this is the encryption method in boring SSL. I'm not going to even try and read that. It's an encryption method. It's unfortunately in C, right? So it has pointers and more sizes and more pointers and sizes than I can keep track of. So first, let's just update this to C++ so that we can kind of look at it in a little bit more of a coherent form. So this is the exact same API updated to use basic C++ things, okay? Didn't change the structure or shape of the API. This is a trivial kind of update to make. So what we can see is we have this input, and this is the plain text that we want to encrypt, right? And we have this output, and this is where this is a buffer we're supposed to populate with the ciphertext, right? This is a mutable buffer. And the API documentation, if you read the documentation for this, says that this input buffer and this output buffer are allowed to alias, specifically when they are the same. Because this API can either do in-place encryption or not. That's really challenging for Rust. This basically makes this shape of API completely unamenable to Rust in any form. Like you don't migrate this API in this shape to Rust. To make matters more complicated, there is also this output buffer called outtag that does not alias anything else, right, according to the contract. So how can we migrate this to Carbon, and how can we use this more expressive model? So the initial kind of trivial migration to Carbon, and this is to kind of our expected safe, memory safe Carbon, is that we add an alias set parameter or a loan parameter. Like I said, this is still very fresh. I don't know that we have our terminology figured out here. But we have some parameter that we're going to use to track which things can alias each other. And then we can apply it to all of the pointer-like things, like the pointers themselves. We can apply it to slices, right? And we can say that, I see. So if I apply it to all of these, then I know that these input parameters and this output parameter, they have the same alias set. They might alias, right? And so I don't get to assume that they don't alias. This is kind of a conservatively correct way of modeling this API in Carbon. Okay? But it's not really modeling all of the API. For example, outtag is not allowed to alias any of these things, and we haven't modeled that. And that means that callers might accidentally violate that part of the contract. So let's actually improve this, right? What we want to do is recognize that it's this input and output parameter that are allowed to alias, not any of the other things. So we can give that a distinct name, call it inout, right? And we can then mark that the input and the output have that alias set. For all of the other pointer-like things, right, like this outtag that are not allowed to alias, we can still support them, and we maybe have a special syntax to say its own custom alias set. Doesn't alias with anything else. Right? And this gives us a more precise way of expressing this. And because we have this ability to both control aliasing and to have shared mutability, rather than exclusive mutability, this is something that we think we can model directly in Carbon. Okay? Now, if we look at what this looks like in Rust, like I said, this is actual real code, so we have a Rust version of this API. I just want to emphasize how different the structure is. Right? We actually have two separate Rust APIs. One of them takes the plain text and returns the ciphertext. The other one is the in-place API, and it takes a mutable buffer that it always replaces with ciphertext. Okay? And so this is the kind of structural difference that you're required to do. Now, here's the big thing. I'm not saying this is a worse API. In fact, I will absolutely say I prefer this API. I think this is a way better API. I love it, right? That's not the point. This is a great way to build the interface. The thing that Carbon is allowing us to do is it's allowing us to decouple restructuring the API into this better form, which hopefully someone will do it someday, from actually annotating it in a way that demonstrates and proves it's memory safe. Right? This way we can do those in either order, whereas with Rust we kind of have to either do them at the same time or strictly order the restructuring before we try and migrate it to Rust. And that makes migrating between C++ and Rust much less incremental, right, and much harder to deploy. Not all mutations are sound with this aliasing, so I do want to touch briefly on where exclusivity comes into the model. So let's take another real-world example, though, because, again, it's great to have real-world examples that are motivating us. This comes from the Dawn project, which I don't actually know anything about, but found some excellent example code in it. We have two methods on this class device space. Okay? One of them gets this internal format. This returns a pointer to a format that is actually inside the object, right? So this is actually returning a pointer to some internal data structure, okay? And then we have a separate method called emit warning once. And this is actually updating a set in the object, a set data structure. And when you insert into a set data structure, that can invalidate any pointers into that set data structure. So this is what we might call a shape-changing operation, because it invalidates existing pointers and handles. Now, fortunately for us, the implementation happens to have a totally separate implementation for the format pointers from the set. But there's nothing in the API that promises that, right? That's not actually something we can rely on from the API design here. And so there is a real risk when we're using this API of getting a bug. Let's look at a call, right? We get this format pointer. We then call this shape-changing operation, right, which is going to insert something into the set. And you can even see, this is actual code from the project. Later on, we use that format, okay? And this is a potential bug. We're using a pointer into an object after we've done an operation that, as far as the API is concerned, might have invalidated all pointers into that object. Right? If we stored these formats inside the set data structure in some way, this wouldn't work. So how do we actually migrate this to Carbon? How do we express this kind of API constraint? Because shared mutation is not going to be an acceptable way of modeling this. Well, we have one place where we do use ref, but we don't use just ref. We actually use ref to a constant object, because we don't need to do mutation here. What we need to do is return a pointer into ourself. Okay, and so this is kind of the alias set notation again, but it's saying, the alias set we're part of is actually the current object, right? So now we know that this is returning these internal pointers. And when I say pointer, just to be very clear, I don't mean unsafe. I know pointers are almost always unsafe in Rust, but this is actually something we think we can make a safe pointer in Carbon. And now when we get to the shape-changing operation, we're going to have a ref. But we're not just going to have a ref. We're going to say that it is exclusive. We explicitly say this has to be exclusive. All right, and that's because we're going to do a shape change. And now when we go to the migrated call, right, we're going to have to update that caller to also have exclusive access. Otherwise, it could never call the shape-changing operation. We're going to get format, right? We're going to get a pointer. This is a safe pointer. We don't have to write the set annotation here. It can be implicit. We can learn from that. Right? But now we know it points back into device. And that means when we come down and we do the shape-changing operation, we actually know that there's a problem. And in a strict memory-safe compilation model, we can reject this because the API did not give us a good enough guarantee. It said it needed an exclusive access to the object, and we have another pointer into that object live right now. But Carbon can also potentially have a permissive compilation mode, which doesn't reject this, right? It knows that there's been a potential error, but maybe it doesn't reject it. And we'll come back to why that's useful. Well, what would this look like in Rust? Right? In Rust, it looked fairly similar. You'd have format here. It would be a shared borrow into the data structure instead of a pointer. But we would know that shared borrow points into the device object, right? We come down to do the shape-changing operation, and this would require a mutable borrow, an exclusive mutable borrow, and it would get rejected. Like, Rust won't compile this code, right? And so this does get rejected by Rust. But if you're doing a migration from this C++ code into Rust, you may not want to change the structure of this code on the first iteration, right? Your first iteration, you may just want to port it into the Rust syntax. There's not a great way to do that with Rust, but there is a way, okay? How do we do this with Rust? We use unsafe, of course. Like, this is why Rust has unsafe. Okay, so let's do unsafe. So we get our format. It's not a shared borrow anymore. It's a raw pointer in Rust, right? So this is not safe. We have to do some shenanigans to turn that shared borrow into a raw pointer. But now we don't have this shared borrow lingering around, so there's no problem getting a mutable exclusive borrow to a device. We can do this. We can do the shape change operation. And then we can use unsafe to dereference the pointer. But we have a problem. Because we've dereferenced this pointer after it was invalidated by taking a mutable borrow, if we run this through Miri, it actually complains this has undefined behavior. Now remember, the implementation in C++, these are two different fields. They don't interact with each other at all. This code does not have a bug in it in C++. But when you migrate it to Rust using unsafe, you introduce a bug, right? And so the really nice thing that we can do with Carbon here is we can allow the code in a permissive mode, but more importantly than that, we can say that this is not UB. Right? We can actually say that, like, no, we're going to assume that somehow this is actually well-defined, that you had the implementation designed the right way, and that format pointer did not become invalid. Right? This is a big change. Right? It's a much more relaxed model for what unsafe code means. And so that's actually another really big change that we think we can make that's going to allow us to approach the brownfield. OK, so that was a whole lot. But I hope you're starting to see this pattern that emerges, right? Carbon ends up being very different from Rust, right? We're designed around the needs of this most brownfield, large-scale C++ use cases. We end up really well tailored to those use cases, not to all use cases, but specifically for interop and for migration, right? And that does not come free. And so I'm not suggesting that everyone should design their language this way, because this comes at a cost of complexity. Right? Basically, everyone thinks that this is Rust versus Carbon, right? Like I know that this is in everyone's mind, but I think this is actually the wrong mental model. It's not about this, right? This is actually about simplicity versus complexity. All right? And simplicity is actually good, right? And often better. But it's also about hard migration versus easy migration. This is a trade-off. This is a classical trade-off. There's not one right answer here. There are two incredibly different trade-offs to make in this space, which takes me back to my spectrum, right? This is why I'm really excited about this approach to getting memory safety everywhere, because we're making radically different trade-offs to go after the radically different use cases that we have. That doesn't mean we don't move towards the center. We have to cover the whole space. Right? Remember, it's everywhere. But it means that we can be much more effective at going after memory safety everywhere by kind of working together. So thanks, everybody. And I'm happy to take any questions that folks have. Questions? I see one hand. There are microphones. There are microphones on the aisles if you want to get up. I can at least one.
Hey, great talk. With regard to Carbon's safety strategy,
yes.
Is the intent to mark some functions safe and unsafe? And also, is there the intent to incorporate a borrow checker into it?
Sure. In reverse order, is there going to be something like a borrow checker? Absolutely. You have to, right? Whenever you're modeling kind of these invariants, aliasing and lifetime invariants in the type system, you need the type system to verify that they're correct, right? So that's a definite. Are we going to mark functions as safe versus unsafe? I suspect yes, but maybe with different markings than you're imagining. So we have two different things that we want to track here. One are unsafe operations, and those are things that the type system could not determine were memory safe for whatever reasons. Those are things we want to mark as locally as possible, right, at the actual operation. So a call to a function that is inherently memory unsafe, that might be an unsafe function that you have to mark as unsafe. There's a second thing we want to do, which is how many of these unsafe markings do we require given the state of migration from maybe an unsafe original code base? And that's kind of an orthogonal question. We're calling that the strictness as opposed to the safety. Because it doesn't change the safety model, right? The operations are still just as unsafe before or after. But we have different strictness levels that are going to determine how many of these markings you have to make explicitly in source versus being able to elide because you came from a memory unsafe programming language. And we're thinking that that strictness is going to be much more coarse-grained, probably function boundaries and file boundaries, probably not more fine-grained than that, because it is just a strictness marking.
Thanks.
Is there going to be some kind of equivalent to the sync and send traits?
So going to be some equivalent to sync
So
and send for concurrency.
Yeah,
I
for
have to
concurrency.
imagine so. I don't know what they look like. We're just getting started on the safety thing, but I have to imagine so.
Okay.
Thank you very much for the talk. I feel like this really helped me understand what Carbon's trying to do and where it fits in. I'm wondering, it sounds like this is a great way to start a code base moving from very brownfield towards something nicer and more memory safe. How do you envision code bases then going from something a little nicer to maybe something a lot nicer, so maybe addressing that API to be a little more provably safe?
Oh, that's a good question. I mean, I think the more, like the deeper the change you want to make to the structure of an API, the more expensive it is to make that change. The more tooling you need, the more capabilities you need to kind of access all of your users, to update them. I don't know how we solve that problem completely. We are thinking about that, and whenever we see an opportunity, we're trying to add language features that kind of make that easier. Most of these are things that allow you to start making the change and then kind of asynchronously accumulate it so that you don't have to make a kind of large synchronous change. I think there are a bunch of language features like that that kind of help you do these kind of large-scale improvements. I think Rust also has great features here, though. This isn't a place where I think Rust is lagging behind. If anything, I think Rust is kind of at the forefront of these kinds of like healthy refactoring techniques being available.
Thank you very much.
One more question. OK, last one.
Thanks. So one thing I'm really curious about is that Carbon's been in the works for a few years now. And one thing I'm curious about is what the incrementality of that migration story actually looks like, right? You're prioritizing brownfield, and so you need to be able to move stuff over incrementally. And what I haven't heard yet in the world, I haven't paid a lot of attention, but I imagine that this is a thing that your team is putting a lot of time and effort into.
The incrementality we're looking for is basically a header file and its source files. Right, and as fine-grained of header file and source files as you need. We're even hoping that you can migrate a header file and its source files, but not the unit test. Keep the unit test in C++ and test that the migration actually worked. And then maybe migrate the unit test as a second step.
So their translation units are going to be one-to-one compatible?
That's the goal,
almost?
yes. All right.
All right, thank you, Chandler.